Thanks, Valerio. Okay, so the title of my talk is Definity Reductions in the Context of Non-Local Games. And this talk is based on two different papers. Okay, so the first one is Definity Reductions for Correlation. This is a joint work with Renato Renner. And the second one is an application of that paper called Non-Signaling Parallel Repetition using Definity Reduction. This is a joint work with Renato and also Thomas Vidic. Okay. So the outline is the following. I will start by presenting non-local games and the parallel repetition question, which is related to those games. Okay, then the second part will be devoted to definity theorems in the context of games. So I will explain what are definity theorems and how those can be used to prove parallel repetition results. Okay, and also what are the difficulties there. Then show you the results. And I don't think we will have much time for the proof ideas and techniques, but maybe keep it to the end. Okay, so games and parallel repetition, you're all familiar with this setting. It's a general way of thinking of Bell inequalities, for example. So we have several different players, okay, sitting in different rooms, and they're not allowed to communicate. And we have a referee who is managing the game. Okay, so the referee is going to send each of the players a question, and then the players, they need to reply with an answer. Then the referee sees all of the questions and answers together, and decides whether the players win or lose according to some winning condition. Okay, so this is really like a Bell inequality or a CHSH game or something like this, if you like. Okay, mathematically, we define a game with a set of possible questions, a set of possible answers. Then we have a probability distribution over the questions according to which the referee is choosing the questions. And some winning condition, this is just a function from the questions and answers to 0, 1, stating whether this particular answer is good for that particular question, for example. Okay? And of course, the goal of the players is now to win the game as good as they can. For this, they can decide on a strategy in advance. Mathematically, we model this strategy by a conditional probability distribution. We denote it here by O of A given Q. So for every question, we have a probability distribution over the answers of the players. And depending on the specific scenario, we can have different conditions on this conditional probability distribution, on this strategy. So for example, if the allowed resources are just classical, then as you know, the players can have some local functions. So each player will apply a function from his questions to his answers. Okay, plus they can have some shared randomness. Okay, this is exactly like the local hidden variable explanations. And this defines us a possible set of conditional probability distribution of strategies out of the entire space. And of course, we can have a more general strategy, a quantum strategy. Okay, then the players, they are allowed to share some entangled quantum state. And when they get a question from the referee, they can make a measurement on their part of the system and base the answer according to the measurement outcome. Okay, and this gives us a larger set of possible strategies. And the most general thing that we can consider in this setting is what we call the non-signaling strategies. Okay, so these are all the strategies, all the resources that do not allow the players to communicate using those resources. Okay, so for example, it means that each player cannot infer from his part of the system what were the questions that the other player got. If he can infer, then it basically means that the questions were somehow communicated to him. Okay, and this is signaling. Okay, so of course, if we don't want to let the players communicate during the game, this is the most general thing that we can consider. And this is also what I will consider in the parallel repetition result later on. Okay. So what is a repeated game? We still have the same players and the same referee and the same game in mind from before. But now the referee is going to choose n independent questions to the players and send them all at once. Okay, so he sends a vector of questions to each of the players. And the players now, they need to answer with a vector of answers. Okay, again, all at once. And then the referee is going to go over each of the indices of these vectors, okay, each of the subgames, and see in each subgames whether they win or lose the game. Okay? The goal of the players is now to win as many coordinates as possible in this repeated game. Okay. So again, the big question is how well can they do? So of course, one possible strategy they can have is the trivial IID strategy, independent identical distributed strategy. So if O of A given Q is an optimal strategy for one game, then of course, then they can just play each of the games independently, and this will give them some winning probability. Okay? But since the players get all the questions together, they can actually do something more complicated than this one. Okay? They can create some correlations between the different subgames. So for example, the first player can decide to answer his first question according to the question he got in the third subgame. Okay, and by doing this, he makes correlation between the different subgames. Okay, and we denote this kind of more general strategy by P of A vector, Q vector. Okay, so this is any strategy for the repeated game, not necessarily with this type of IID structure. Okay, and indeed, it seems weird, but this can be useful for the players. So for example, if you play the CHSH game with a classical strategy twice, you can have better strategies when you correlate the different subgames than just playing them independently. Okay, so it's not something to just forget about. Still, what we can ask is once we have many subgames, okay, many repetitions of the game, can they do significantly better than this IID strategy? Okay, can those correlations between the subgames really help them to do much better than this trivial option?
The goal is to win them all, right?
Okay, so this is the next slide. So this is the non-formal version of the question, and now we can try to do it more formally, and then we have two different versions. So if we denote the optimal winning probability in one game by 1 minus alpha, okay, this is just one game, then now we can have two different questions. The first question is what we call the parallel repetition question. Okay, the question is what is the probability to win all the games? Okay, so using an IID strategy, if the optimal winning is 1 minus alpha, then IID will have 1 minus alpha to the n. Okay, and now we're asking, can they do with a correlated strategy much better than this 1 minus alpha to the n? This is the parallel repetition question. The second question that we can ask, a bit more general, is what is called the threshold theorem question. Okay, so here we're asking what is the probability to win more than a fraction 1 minus alpha plus beta of the games, of the subgames. Okay, so for example, for IID strategy, Chernoff bound tells us that the probability to win more than this fraction decreases exponentially fast with n and beta squared. Okay, with the number of repetition and this constant here. Okay, so now we're asking, can they do much better than this type of decrease? Okay. So since we are in a trustworthy cryptographic conference, so how is this related? So there are different connections. Here are two of my favorite connections. So first of all, parallel repetition, even in the classical world, in classical cryptography, this is used as a technique to amplify soundness and security of protocols. Okay, you just want to repeat now something many times, but perhaps all at once, such that your resources will not somehow explode. Okay, so this is something that you use in this setting. But also for us, I don't need to convince you, this is a way, considering parallel repetition is a way to somehow investigate and understand the structure of non-local games and of correlations for these non-local games. Okay, so, and these games are relevant for all the device-independent protocols that we have. Okay, so this parallel repetition question allows us to understand such questions about these kind of larger correlations. Okay. Some related work. So this question of parallel repetition is known for a long time now in the classical world. So there are many previous works even to this one. But this work by Raz in '98, this was the first exponential result. Okay, so he proved that for classical two-player games, there is an exponential parallel repetition theorem. What does it mean? It means that the probability to win all the games decreases exponentially fast with n. And then his proof technique was used in many more papers, many more works. So Holenstein, for example, took the same proof technique and extended it also to the non-signaling case, to two-player non-signaling games. Okay, later on. Rao also simplified a little bit in the classical case and added also the classical threshold theorem. Again, same proof technique. And recently, Burman et al., they again took the same proof as Holenstein, but extended it to multiplayer non-signaling games. Okay, and plus the threshold theorem, this holds only for complete support games. This is something that we have as well. I will address it in the end. Okay, so all of these works in the non-signaling and classical case, they're basically, they follow this kind of approach. In the classical case, there are also a bit of a different works, but these are the main things. Maybe just a word about the quantum case. So in the quantum case, also there are many recent works, but we don't have yet a general proof for parallel repetition in the quantum case. So we have only proofs for a specific type of games. Good. So now we're in the second part about the Finetti theorems in the context of games. So in the Finetti theorems, the way I see it at least, there are two main ingredients. The first one is what we call a permutation invariant state, and the second thing is the Finetti state. Okay, then the Finetti theorem is basically just a tool that connects these two ingredients. Okay, so let's start with the ingredients, and then we will see the tool. So what does it mean, permutation invariant? So imagine that we have some state, and this state has many different subsystems. Okay, we said the state is permutation invariant if when I permute the different subsystems, everything looks the same. Okay, so more formally, in our case, for conditional probability distribution for strategies, okay, this is what it means that a strategy is permutation invariant. So for every vector of answers and vector of questions, okay, I permute with every possible permutation pi, I permute the vector of answers and the vector of questions together in the same way. And then my strategy after the permutation, my strategy before the permutation looks exactly the same. Okay, so this is permutation. If this is true for every permutation, then the strategy is permutation invariant. Okay, if you want to think about boxes in your mind, a device-independent setting, so this is like we have one big box. So here we might have some correlations in between. Okay, we don't have any non-signaling conditions between them, but we have these different inputs and outputs to the box. Now the fact that I'm permuting the two vectors together, this is just like I'm permuting the inputs and the outputs in the way that I'm basically permuting those boxes. Okay, so for those who are used to boxes. Okay, why permutation invariant? Well, permutation invariant is a symmetry which is very important in physics. So first of all, we do see it quite a lot. So for example, if we have many photons here, we cannot distinguish the different photons. Therefore, if I just permute the different photons, two of them, you will not see any difference. The state is the same. So we have it quite a lot. But even apart from this, it's a symmetry which is very easy to enforce. Okay, so in the cryptographic scenario, you don't want to assume that you have permutation invariance, but in many cases, you can really make sure that your state is permutation invariant by just permuting, for example, all the different subsystems, or enforcing some conditions about your protocols. Okay, so then this is a symmetry that we can have also in the cryptographic setting, and this is why it's very useful. Second ingredient, the Finetti state. This is just a name for a state which has the form of a convex combination of IID states. Okay, so again, in our framework with the strategies, this is the structure. So O is a strategy for one game. Okay, then O to the N is the IID strategy. Okay, so this is this IID states. And now I have a measure here, DO, which assigns different weights to the different one-game strategies. Okay, so this DO, this measure, together with the integral, gives me the convex combination. Okay, to be more concrete, this is an example for the Finetti strategy. Okay, so here I have two types of IID strategies, O1 to the N and O2 to the N, and then my measure just assigns, for example, 3/4 to the first one and 1/4 to the second one. Okay, so this is the Finetti strategy. It has this particular form of convex combination of IID. Why do we care about the Finetti strategies? Well, because they have a very simple structure, and therefore they're very easy to analyze. Okay. Now, the Finetti theorem is this tool that connects these two ingredients. So we start with a permutation invariant state, and I argue that usually it's easy to have. Okay, so it's easy to start from that point. And now we are going to use the Finetti theorem, which will allow us to basically analyze only the Finetti states, which are easy to analyze because of their structure. Okay, so this is the idea. And this type of connection, the Finetti theorems, there are many different Finetti theorems with many different forms. Okay, many different ways to go from that direction to the other. And indeed, they are very useful in many applications in quantum information theory. So, for example, in cryptography, this is the Finetti theorems allow us to basically do a reduction of the security. Instead of proving security against a very general attack, we can prove only security against very simple attacks where the adversary actually attacks each signal in exactly the same way. Okay, and this simplifies our lives quite a lot. Okay, then it can also be used in quantum tomography, channel coding, and many other applications. Back to our games, what do we want to do now in the game setting? So we want to start with a permutation invariant strategy for the players, which is easy to have. Why? Because the repeated game is actually permutation invariant. Okay, so the referee is asking the questions in an independent way, and he's checking the answers for each subgame independently. So actually, if we just permute all the questions, all the subgames, everything stays exactly the same. The game is not harder or easier for the players. Okay, it means that we can assume that the strategy the player have is already, it's already permutation invariant to begin with. Okay, so it's easy to be in this side. Then we want to use a Definetti theorem, which will allow us to basically go to a case where we only need to analyze the Definetti strategy. Okay, in this case, it's easy to analyze. Why? Because the Definetti strategy, they have this trivial structure of convex combination of IID, and IID strategies behave trivially under parallel repetition. Okay, so this is very easy to analyze. And if you think about this, is exactly what we want to do. We want to show that any permutation invariant strategy or any general strategy for the repeated game is more or less as good as a Definetti strategy. Okay, so this is a very natural fit. So indeed, if it's so natural, how come this was never done before? Well, the reason is that all previous Definetti theorems, they had certain assumptions which made them irrelevant for this kind of setting, okay? For the device-independent setting or to this parallel repetition setting. So for example, quantum Definetti theorems, in all of them, we have dependency on the dimension of the underlying states. Okay, and as you know, in the device-independent settings, when we are interested in correlations, we don't want to restrict the dimension. We don't want to say that the players must share a state with a specific dimension. So we cannot use them. Okay, but even more, as also Marco mentioned, okay, we have, actually in order to prove the Definetti theorems, we have to already assume some subsystem structure. Okay, so, and once we're dealing with those games, or in the device-independent cryptography, again, we have some big box and we don't know what's going on inside, we cannot assume to begin with that we have this subsystem structure. Okay, so we couldn't use all of the previously known Definetti theorems to do all of this. But fortunately, we have a recent Definetti theorem, we call it Definetti reduction, which holds for correlations, and therefore we can use it. Okay, so what are the advantages of this new Definetti theorem that I'll show you in a minute? So first of all, there is no dimension dependency. Okay, instead of the dimension dependency that we have in the other Definetti theorems, we have the number of measurements and outcomes, or the number of questions and answers in a game. Okay, so this is something that we know. And we don't have any non-signaling assumptions between the different subsystems. The combination of these two make this new Definetti theorem applicable to the parallel repetition question, as we will use it now, and in general to the study of correlations. Okay. So what is the theorem? So this is just a reminder of what it means a permutation invariant strategy and what does it mean a Definetti strategy. Okay, now the Definetti theorem, this is the following theorem, is this inequality. Okay, so there exists some Definetti state such that for every permutation invariant state, this is true. And here we have every possible vector of answers and questions. So these are just numbers on both sides of the inequality. Okay, here we have the probability that the permutation invariant state assigns to this vector of answers given this vector of questions. And on the other side, we have the probability that the Definetti strategy assigns. And then we have this prefactor here. Okay, n, just to remind you, so n is the number of repetitions, okay, number of subgames. M is the number of questions or measurements per box, if you would like. And L is the number of answers or outcomes per box. Okay, so this is the reduction. Let's try to use it to prove parallel repetition. So the first trivial thing that we can try is this inequality, which follows from the previous inequality that I showed you. So the winning probability of the permutation invariant strategy, okay, is smaller or equal to this bound here times the winning probability of the Definetti strategy. Okay, so this is very nice. If we can prove that the winning probability of the Definetti strategy now decreases exponentially fast with n, then basically we are done, because here we have exponential decrease with n, and here we have just a polynomial increase with n. Okay, so the exponent dominates the behavior, and that's good for us. Okay, so that could have been very nice. Unfortunately, it's not useful, so this is correct, but we cannot really bound this by an exponentially small thing, and the reason is the following. So when we prove the Definetti reduction, okay, the inequality that I showed you before, we actually have a Definetti strategy here, which is signaling. Okay, what does it mean? So this is the structure of the Definetti strategy, and here we have this measure here. This measure goes over all possible conditional probability distribution, okay, all possible maybe strategies for one game. It also includes strategies where actually the players are signaling, okay? Also signaling conditional probability distributions. So it means that if the players now they want to simulate those strategies, they will have to communicate between them. Okay, so these are not a valid strategy for our games. We are not allowing the players to communicate. And since we also include here those invalid strategies, then we cannot just trivially say the winning probability here of this strategy decreases like 1 minus alpha to the n. Okay, so this is a problem. So yeah, we might say, okay, maybe the definite reduction is just not that good. Maybe we can find a better definite reduction. So if I know now that my permutation invariant strategy is also non-signaling, and I have this promise, okay, okay, then maybe I can find a better definite reduction where the definite strategy will also be non-signaling. Okay, that can be very nice. It will solve the problem from the previous slide. Unfortunately, we now know that this is not true. We cannot have such a thing. So there are actually, from studying parallel repetition, so there are counterexamples. There are games where the players can really make small correlations between the different subgames, and this allows them to increase the winning probability in a way that will contradict the bound that we get here. Okay, so this bound, if such a thing existed, then we will get a too strong bound for parallel repetition that we know cannot exist. Okay, so this is impossible. The same is true for quantum or classical. Okay, so we cannot have quantum here and quantum there, or classical here and classical there. Okay, it's not something special for the non-signaling case. Okay, it really means that once we want to prove such a definite reduction on the level of the correlations, you must go outside of the allowed set of the correlations. Okay, you cannot just stay in your set. So we have to deal with this signaling definite strategy. Okay, there is no other way. So just to give you a little bit of flavor, what are we doing? So let's assume that our strategy looks more or less like this. Okay, like this definite strategy. What we show is that if in total this thing is non-signaling, then the weight that this measure assigns to signaling stuff is exponentially small in n, in the number of repetitions. Okay, so everything in total is non-signaling. We still might have signaling parts, and they just in total they cancel each other. Okay, so it might be that we have some signaling weight here, but it must be exponentially small. And then what we can do, we can treat this exponentially small part as an error. Okay, we just forget about the signaling part, and we analyze easily the non-signaling part. This is like the general idea of how the proof works. Okay, how we still deal with this signaling definite strategy. Okay, so just to state the result, a bit more technical. So any complete support non-signaling game. So what is a complete support game? It just means that every subgame, the distribution for the questions for the players, there is non-zero probability to ask any combination of the questions. Okay, this is basically connected to the way we define non-signaling conditions. Okay, so it's really related to that thing. So every such game with optimal winning probability 1 minus alpha, any beta and any large enough number of repetitions, this is the threshold theorem. Okay, so the probability that the winning frequency is larger than this 1 minus alpha plus beta is bounded by this thing. So let's start with the exponent. Here we have some constant depending on the game. Okay, and then we have n beta squared. Okay, as I told you before, for IID strategies, Chernoff bound tells us that this is the optimal dependency. So actually, this is the optimal dependency in general. I think this is the first work that shows this optimal dependency. So this is the exponent. Then we have here the polynomial prefactor that comes out from the type of proof. Okay, so this is polynomial in n, and depends also on the game. But indeed, the exponent dominates the behavior of this bound. Actually, even more so, in a paper that appeared last week on the arXiv, you can see that there is actually a very simple trick that can allow you just to get rid of this polynomial in the end. Okay, so after you do the entire thing, you can just say, okay, forget about this one. Okay, so this is a very nice thing. We can apply it as well here. Okay, and then you're just left with the exponent. Second theorem, okay, it's just the same as the previous one. We just try to get rid of this complete support thing. So the first theorem also holds for two-player games without complete support. So for two-player games, we can fix this in a sense. For other players, if you have more than 2 players, then yes, this is not the case. Okay, so you just have to do a different modification to the repetition of the game. So we just add some dummy questions such that basically we make it complete support. Okay, but yeah, maybe less interesting for us. Okay, proof ideas and techniques. So I'll skip most of it. So maybe just to repeat that part. So the general idea is that if we have this total strategy, okay, first of all, we need to define some signaling measures so we can in a meaningful way say whether a system or a strategy signals a lot or a bit. Okay, after we do this, we prove that the weight on systems that signal a lot is exponentially small. This we do with a reduction to some guessing game that I won't have time to explain now, unfortunately. And then the second step is to now we have only the systems which signal just a bit. And with those systems, what we're doing is we're just saying, okay, the winning probability is not that far from this 1 minus alpha, okay, from the optimal non-signaling probability. This you can do with sensitivity analysis of linear programming. Okay, so this, I jump. So this is the guessing game that we have. Okay, sorry. Okay, so let me summarize. So first thing I showed you is a new proof for non-signaling parallel repetition using the Finetti reductions. So I told you in the beginning, most of the other proofs just follow the same proof by Raz. So this is a completely different thing, which somehow gives a bit more intuition as to why we have parallel repetition. Okay, the Finetti theorems, they fit very naturally to this setting, and this is the first time that we could actually prove such a result with the Finetti theorems. Okay, and of course, a big open question is what about classical and quantum parallel repetition? Can we do something similar? Okay, so this is something we are working on now. It's a bit more complicated. And apart from this, and maybe in this context, this is also a first new application for the Finetti reduction. So the Finetti reduction, as I showed you, it has advantages over the previous Finetti theorems in the sense that we can use it to investigate correlations or the device-independent setting. Okay, so a big open question for me is what more can we do with it? Okay, can it play an important role in the device-independent cryptography, like the other Finetti theorems play an important role in the standard device-dependent cryptography? Can we do randomness amplification with it, and all the other things? Thank you very much.
So in the case of the non-signaling parallel repetition, it's a new technique which has lots of potential for other things. But just to be sure, at the moment what you proved with it was known already, right? Or is it stronger than what was known?
So, I mean, it was known, but then you need to compare the parameters, right? So I think, yeah, maybe the optimal dependency of n beta squared is, I think, the first time. Also in the classical parallel repetition, I don't think this is known. So this is the first time that I think someone achieves this optimal dependency. And then, yeah, well, compared to this other work that I mentioned by Burman et al., you can try to compare the different bounds. They're very similar. The different constants that we have, they're very similar to one another in nature. So, yeah. But the general thing, yes, it was known that for multiplayer games, for non-signaling multiplayer games, complete support games, we have this type of thing. Okay, so this was known just with the old proof techniques.
And how far would you say that you are to using these techniques for the quantum case? That's a trick question.
Yeah, well, yeah, I cannot answer this. Until I'm in the end, I cannot say that I'm close, right? So, yeah, we're working on it. Hopefully it will work. Yeah. Okay.